this afternoon. So this session is kind of different flavor from what you have had previous few ones. We're gonna mainly talk about existing challenges in areas we need more active research. And another big difference is here, many of these are still like open-ended. There's no definite answer of like, or the best practices or definite, guidance of how you should tackle these problems. I hope, audience in this group can, we find things interesting and even some ideas related to, your expertise that can be useful and we can share and discuss. So I'm gonna just a non-exhaustive list of challenges: metric sensitivity, problem with hypothesis testing, and p-values, which actually occurs a lot in the whole day, the tutorial this morning and also this afternoon. Continuous decision making, sequential testing. If time permit, I'm gonna go in more detail about the effect heterogeneity. Because so far we mainly were focusing on average treatment effect, but people all know that there's a lot of difference between units to unit, person to person, and also across time, things might change. And there's some other topics I'm not gonna touch today, time barrier effects, and how long should we run experiments? Is 1 week, 2 weeks enough, or should we run things like months? Especially if there's some delay in the effect. If you introduce something too fundamentally change the UI, people might need some time to get used to the change, so you will see some delay. And a tough problem is in terms of leakage and violation of a very fundamental assumptions, which is called stable unit treatment value assumption. It appears in a lot of cases, especially network. So if you're working on a social network or some treatment effect that might change, heavily depends on your neighbors, your friends, whether they're in treatment or in control, and these kind of cases, this leakage effect might be a big issue. Okay. And the list can goes on. So metric sensitivity. We were focused. We talk a lot about statistical power, but what is metric sensitivity? People typically think sensitivity is just statistical power. In fact, it's not just about it, right? There's two components. If you think about a sensitivity as intuitively the probability that you can detect a true effect, a true movement that you introduce. Okay? You can decompose that into two parts. First, given there's a change, there's a movement, what's the chance you can detect that? Based on the configuration of experiments, based on this set of sample size, based on this range, how long you run the experiment, what is the chance you can detect that? And the second part is just purely how likely you're actually introducing something that have a true movement, right? The type of ideas you generated, how likely this is significant enough so that it uses behavior. And statistical power only quantifies the first part. Okay? And there's also a lot of cases, the second part, which is how good is our idea, that reveals the more intrinsic sensitivity of the metric responding to the type of experiments, type of ideas we are testing. So when we talk about a lack of sensitivity, right, we think some metrics is just not moving. It's important for us to understand which part is lacking. So the first case, we need to improve statistical power. Okay, so we know that we have some successful effort that we didn't move some metrics, but we wasn't able to detect this in a statistically significant manner. And a natural reaction to increase power is by you can just increase sample size, okay? And increase the traffic size. So in case but this has a hard limit, right? You can only use as much as 100% of the user base you have. So once you reach to the 100% user base, what can you do? You can also try to run experiment longer. But what surprised us is that, sometimes run experiment longer won't always help. I'm gonna explain in next slides a concrete example of that. And you can also try to reduce variance. By reducing variance, you will improve your statistical test sensitivity with a pure power increase without needs to run things longer or needs to introduce some more users. And the last thing you can do is you can change the estimate. What they call estimate is like what you're trying to estimate. Okay, typically people do this average treatment effect, but there are some cases that the average itself is hard to detect, so you can do something like transformation and capping for highly skewed metrics. But once you're doing these kind of changes, you need to understand that you need to interpret with extreme caution, because you're actually changing the thing from a very, very easy to understand average into something that's kind of after some transformation. You can also try to use some non-parametric tests, such as rank sum tests, but that will also make things harder to interpret. Okay, so why run experiment longer won't always help? So this is a concrete example where Pablo mentioned that session per user is not very sensitive. So if we look at the t-test, right? T-test is basically the difference, the delta here, divided by some standard error. This is proportional to the percentage delta, the percent change you're making, times the sample size divided by the standard deviation over mean. Okay. So to reduce variance, so you can increase the t-statistics by reducing the variance of delta, so that will increase the power. But the variance of delta without changing definition of delta, you can reduce it by just increasing the sample size, which is on the numerator of the last term. However, when we run experiment longer, we're also changing the distribution. Think about people have on average, let's say 10 queries per week. If you run experiment for 2 weeks, this mean changes. On 2 weeks, people might have 15 queries per week. And also, there's more complicated distribution mixtures. There's some users that goes to this website every day. Some users only goes to this website once per week. Some users maybe just once per month. Right? If you run experiment longer, this kind of mixtures of these users also changes. Okay? And what makes things even more complicated is the practice of cookie chain, right? If we try to identify users using a cookie, right, which is highly dependent on how frequently the user click their cookies. So if we run experiment longer and longer, some users might start creating their cookies regularly, and then that will cause us issues in being able to identify users. So what happens for session per user is, in these cases, the sample size and the standard deviation over mean, they both increases when we run experiment longer. And it just so happens that the ratio of these two, they increases at the same pace. So the ratio of these two almost cancels with each other. So when we look at the t-statistics, it's as if, suppose the percentage delta never changed, then the ratio between the sample size and the denominator there remains almost constant. Right? So what it tells us is that even we run experiment longer and longer, we're not actually increasing any statistical power. So that came to us as a big surprise. Okay. So I mentioned another approach is to try to reduce the variance. Okay. And this goes in a very different thinking. So in the previous thinking, where think about we remain, we still look at the same delta, but we try to reduce the variance of the delta. Okay? In this thinking, we say, hey, we're gonna use a different delta. We call it delta star. But this delta star has an interesting property that it has the same expectation as the original delta. In other words, this delta star are estimating the same thing as the original delta. So we're still estimating the average treatment effect in most cases. But however, we notice this delta star has a smaller variance. Okay? And what we want to do is that we're going to build a t-test using this new delta star in place of the original delta, right? So that you can think about the numerator of the delta still on average remain the same, but we have a smaller variance, which also going to increase the value of t-statistics and increase the statistical power. So how do we do that? The motivation is basically, called baseline adjustment. I already mentioned that, there's a heterogeneity in the populations of our user. So think about this mixture model, right? You have these heavy users and very casual and light users, right? They behave very differently. And if we look at certain metric, in this cases, for example, we look at queries per user, we know the heavy users has on average more queries per user, and the light users has smaller queries per user. But these two groups of users, each of them have their own variation within the group, right? But as a whole, we're looking at the mixture of these two distributions, and we're looking at the variance is this, we have this between group variance plus this within group variance. So because of randomization, the proportion of heavy users and light users might be slightly different between treatment and control. So if your treatment has like slightly more heavy users than the control, the treatment might just have bigger queries per user. This is purely due to randomness, due to the randomization. Right? So these are by pure chance, not by the treatment effect, the real effect we try to detect. So if the treatment has more heavy users, in this case, that's a baseline. If the treatment has more heavy users, it will likely have a bigger revenue per users too. And intuitively, we want to do something to adjust it, right? And then there's a very common variance decomposition going on. The variance of the delta of certain metric y we're interested in can be decomposed into these two components. And the second component, which is the variance of the expected, the delta on y given the delta of the baseline, we already know these are the part of variance that can be explained by the difference in the baseline. Okay? So if we can remove this part, we get a smaller variance. So in practice, this is actually quite easy to achieve. So we have this paper published in 2013, which is we define a very simple delta star being the delta of y divided by subtract theta times delta of x. Okay, so this delta star has the same expectation as the original delta, as long as the expectation of delta x is 0. And then we call those x such that expectation of delta is 0. We just call them baseline or covariate. That's a more statistical term to call the baseline. Intuitively, those x are things that we know they're not going to be affected by the treatment we are testing. For example, the proportion of heavy users in the group, right? They are purely by the property of the populations. They're not something that the treatment we introduced will change. So and anything that we know at pre-experiment stage can be considered as those baselines. And then, which theta should we pick? We can just pick the one that minimize the variance of delta star. Because remember, we're trying to construct this new delta star that we want this variance to be as small as possible. Okay, so we just, we call it control experiment using pre-experiment data. Pretty simple. And a small extension, this is just a linear adjustment, and we found it often good enough. But you can, for those machine learning more savvy audience, you can feel like the linear, adjustment is quite crude. So better adjustment can be found by using, try to fit two different regression models on treatment and control separately. So the optimal one is try to find the true regression relationship between the baseline X and the target variance in the treatment group, and also another one for the control group. So if you can find the true regression formula, then this is the minimum variance you can get. And for that, you can use any regression method like boosting, forest. Okay. So what about the case two, right? This is the case one is, we try to increase states of power. What about, the matrix insensitive because you're just not moving it, right? So, you can design a perfect OEC, but if you cannot move it, it's not going to be very useful for you. And so what should I do? So some cases you can re-engineer your metric, which means you just need to find a different OEC. And at different stage of the product, typically what happens is you need to change your OEC. So at the start of a new product, when there's a huge rapid growth of your user base, you can probably use something like your number of active users as the OEC. But once your product gets to a more saturated and mature stage, counting active users are going to be very hard, very insensitive, and very hard for you to move your user base. And then we turn to users success type of metric. And another way you can do is to define a surrogate metric as a function of metrics of other metrics. So this is what we call combo metrics. So you have a bunch of other metrics. They have reasonable sensitivity, meaning that you can frequently see these metrics moved in your experiment. But how to design the functional form of these metrics to combine them together to have OEC. And the challenge here is that a naive linear regression might be a little bit misleading here. To give you a sense of that, remember we're not actually observing the true effect, right? The true effect is unknown. What we observe is the delta of certain metric, which is equal to the true effect plus some noise. So assuming you have two metrics, X and Y, both of these you observe a delta equal to the true movement plus some noise, and attempting to do a linear regression on those deltas observed. But per se, if we have 100 results from just purely AA test, by this time I hope people already know AA test means we know there's no real treatment effect. So in these cases, the real effect are just zero. So what will people expect the correlation of the observed delta between these two metrics? Okay, so if Y is sessions per user and X revenue per user, I would just show you the answer. I would expect these two things to be positively correlated. Why? Because in this case, it's in the AA, and the delta is purely out of by chance, by randomization. So if treatment happens to have more revenue, more sessions per user, I will be more intent to believe there's more, slightly more heavy users in my treatment than control, and they're likely going to generate more revenue too. So this positive correlation is purely coming from the positive correlation of these two noises. They're not correlation from the true treatment effect that we intend to study. Okay, so if, for people willing to see the math, you know that you can actually compute the variance introduced. These are just a common spurious regression that you can find in any linear regression book. Okay. And there's some recent published study try to solve this problem. One approach is to say, hey, if I just do a regression, I know those noises are going to give me some bias. So what if I only look at those highly statistically significant results? So essentially what they do is, if the delta of X is not large enough, I just truncate them to zero. Okay? So this is equivalent to L0 localization method. And there's another kind of different idea. Instead of using regression model, let's just treat this problem as an optimization problem. So assuming we have 3 classes of historical results. Those results we know there's some effect. Those results we don't know whether there's true movement or not. And there's also a set of experiments we know they're AA, so there should be no true movement. And then you just want to search the linear combination of your metrics and try to come up with a new metric that maximizes the test scores in the set that you know there's effects, and also the set that you feel is uncertain, but you want to make sure that it don't give you a lot of statistically significant results in the set of AAs. And the key here is, like I explained, try to differentiate the real correlation between the movement mu and the noises. And you will see this theme come again later. So let's go back to this p-value and null hypothesis state of testing. And this, many research findings are just not reproducible because of the practice of p-value hacking. And many results with small p-values also fails the Twyman's law. It's like you're making some conclusion that that's probably, it's very surprising. And like Ronnie emphasized, instead of celebrating the rational choice, thing we recommend you to do is just to double check your results, or even try to reproduce the results. And it's also an interpretation problem. And it's the common mistake is to interpret p-value as the probability that the null hypothesis is true, given the evidence, given the data we observed. And this is actually came just recently. There's a new article in JAMA, which is a journal of the American Medical Association. It says, and I quote, "This finding did not reach statistical significance because p-value is 0.054, but it indicates a 94.6% probability that statins were responsible for the symptoms." So people, even in this, JAMA is a very prestigious journal in medical research, but even in these kind of top tier journals, people are making these mistakes by interpreting 1 minus p-value as the confidence that something, the alternative is true. And another issue was that, and I didn't see it coming up this morning, is in this framework of null hypothesis testing, there's no way for you to accept the null. Okay, so if your desired result is not to reject the null, and the simple thing for you to do is just to run a small sample experiment that you would, don't have enough statistical power to reject the null. That's it, And I bet a lot of published research, research papers don't even reveal how they do power analysis. Okay, so the key difference here is that what we want is the probability of now being true given the data, but not the opposite, right? The opposite is assuming the null hypothesis is correct. What is the chance that you're going to observe the data like this? And the first one is really the Bayesian posterior belief that the alternative hypothesis, or on the other way, the null hypothesis is right, is true. So this is also closely related to the concept of false discovery rate. And this represents the pair of these, either the posterior of the alternative or the posterior of the null. They represent the real confidence of a correct shift decision. And surprisingly, using this Bayesian posterior, they sort of auto-adjust for multiple testing problem. So intuitively, assuming the metric movements are independent, so intuitively, if I'm interested in this matrix and you're interested in another matrix, and let's just say these two metrics are independent, intuitively, why should I care about your matrix if I only care about my matrix? And I know your matrix and in my matrix, the movement are independent. Okay, so this is actually a good news because multiple testing adjustment is a big headache. Okay, so how do people conduct Bayesian tests? We start with prior odds, which is the ratio of a prior belief that you actually, alternative hypothesis true to the probability the null hypothesis true. And then given the data, you compute something called Bayes factor or likelihood ratio. These two are kind of conditioned on the alternative, what is the chance you're going to see the data, versus the null is true, then what's the chance of seeing the data. And then the last step is just combine these two things by making the belief update. And then you get the posterior odds, then you can calculate posterior. These are just very standard procedures. You don't need to remember the detail. But then the problem with this procedure is, and I'm actually hiding the dirty detail under the copy tail, the slides, is that we don't even know what is this first prior odds. Right? And nobody tell me what is the true probability that I'm actually moving something versus I'm not. And moreover, we also don't know what is the distribution of the data given the alternative hypothesis true. In some sense, we don't even know what is the true distribution under the alternative. Because we know that now is that there's no change, right? But then the alternative is, if we made a change, then what's the distribution of that change? What is the true distribution of the treatment effect? This is also unknown. Okay, so how to get around that? So in a large-scale experiment platform like Bing and Booking.com, we have very rich historical experiment data. So we already mentioned that we run more than 1,000 experiments per month. So over a year, we have more than 10,000 historical experiments. We can use this historical data to try to estimate these unknown quantities. But then the problem is, if you're not lucky like us, if you're dealing with some system that you don't have a rich historical data, so this is sort of like the cold start problem, right? So you don't have any empirical data to help you estimate these unknowns. Then what do? And another problem is, how do you know that those historical experiments are similar enough to the current experiment I'm looking at? Okay. And let me go to the continuous decision-making or sequential testing. So traditional tests also assumes a fixed horizon, like you run for 1 week, and you assume you just gather your data until the end of the week, and then you can compute all different kinds of statistical test statistics. In this cases, I'm using this Bayesian posterior. But however, we also know that the form of this posterior is a function of some sufficient statistics. Typically, in A/B testing, the sufficient statistics involves the sum, and also the count, and also the sum of squares. The sum of squares is used to compute errors. Okay. So that's typically the function of these three stuff. And recently we proved that when the data is observed sequentially, and then you stop the data gathering at the random time, tau. Okay. The functional form of this posterior, but now instead of a fixed time t, you change this to a random time tau, the functional form is still the same. In other words, if you have a code written to do the statistical test for a fixed horizon test, you can use the same code, just plug in those sufficient statistics that gathered at the random stopping time tau, and the math still works. Okay, so the result is actually expected, but it's actually not trivial to prove. This random time tau needs to be a proper stopping time, by the way. Basically, the decision of stopping the experiment has to be made with the observations before or at that time tau. So in other words, you cannot peak. Okay, so you can only use the data up to this time to make the stopping decision. You cannot wait until like 1 day later, and then say, I made a mistake, I want to stop the data, this experiment yesterday, and then I discard the data for the last day, and then, and then report the result using the data end at yesterday. So you cannot cheat like this way. And also this result only works for Bayesian setup. If you want to use the null hypothesis digital testing procedure, there's a different way of thinking, but it's not as trivial as this one. And it also justifies the banded Thompson sampling, which is heavily used in multi-embedded. Okay, so I think I still have time. 2 minutes. So when we say treatment effect, in a lot of cases we just refer to population average treatment effect. So far, that's everything we've been talking about. And we know that effects differs. A feature might be popular in some markets. It might not be popular in some markets. If we understand that might need, leads to some improvement. We can do something different in certain market. Okay? A feature might even be broken, like on one browser. That's a bug that we can fix. And there could be many similar microstructure in populations. In those cases, the treatment effects varies or even can flip side. Like you have positive effect in certain populations, but negative effect in others. So this whole thing is called heterogeneous treatment effect, or HTE. And this is a really hot topic right now, not just in A/B testing, but even more so in economics and government policy evaluations and personalized treatment or personalized drugs. A few examples. We know, in these cases, we are looking at the percentage treatment effect here. You can see that some of the browsers has, has bigger effect than the others. Some of the browsers even is pretty close to 0. And we commonly also observe weekend and weekly difference. Certain features introduced only have a big change in the weekend, but in the weekday the changes are smaller. And one of the examples Paul shared is this sort of shift phenomenon. Like something suddenly happened within the experiment. So the explanation is the experimenters might introduce something to the treatment. They're actually making changes to the treatment, unknown to us. Like when we run experiments, we fail to forbid that the experimenters checking some new changes. Like they can change some side information, or it could be some interactions between this experiment and some other new experiment just started at that time. Okay, and the general framework to think about this problem is called conditional average treatment effect. Okay, so just recall potential outcomes from Lucas' part. You have these two counterfactuals. This metric if you're in treatment, metric if you're in control. We also have a lot of covariates, so based on X, and then also the treatment assignment T, which tells us whether you're in treatment or control. So we're interested in this individual treatment effect, okay, which is the difference between the counterfactual. So given X, so like given your gender, I want to predict what is the effect, given your age, given your household income, things like that. Okay. And we assume there's some true treatment if your counterfactual y1 is some mu1 plus epsilon, and y0 is mu0 plus some delta, and there's some unknown mu1 and mu0 are also unknown. So the best prediction in these cases, if we really know mu1 and mu0, the best prediction of this individual treatment effect will be mu1 minus mu0. So also this is just a regression of this given X. And that naturally leads to so-called meta-learner. From the machine learning people, is it's more like treating these as machine learning problems. If we can fit models for mu1 and fit a model for mu0, and then we basically get the two fits, our prediction is just the difference of these two. Or we can just fit one model that try to model both the treatment and control in the same way. So these are two different schools, but they are sort of coming from the same idea. But the problem here is that in a lot of those machine learning or predictive supervised learning problems, we need to strike a balance between bias and variance. Okay, so most popular machine learning algorithms like Forest, BART, Lasso, they all introduce bias. Okay, if you just predict one thing and knowing the bias, introducing bias is okay as long as you know this bias variance trade-off. However, here we're interested in the difference of these two fits, mu1 hat and mu0 hat. Okay, so what if the introduced bias is systematically different in mu1 and mu0 for certain x? Okay, let's say for women, mu1 hat has a positive bias, but mu0 hat has a negative bias, and that will introduce a seemingly positive delta between mu1 and mu0. Make sense? And so that's the key issue in these two approach. And the recent development is try to treat mu1 and mu0 as not as something that you want to predict, but as some nuisance parameters, and you want to directly model the delta between mu1 and mu0, and then you put regularization and sparsity directly on the delta itself, instead of trying to predict mu1 and mu0 separately. Okay, so these are all called target learning, double ML, or U-learner. Okay, so I'm going to end with this example to help you understand my point. In these cases, I have those red points and the blue points there. The blue points is in treatment, the red points is in control. Okay. If you're going to try to fit these two data sets, right? In these cases, the blue data sets is better be fit by this zigzag lines, so this piecewise linear. But then, from for the blue point, if you look carefully, it seems like it also have the same bump in the middle. People notice that? However, because the blue data is sort of, you have smaller sample size, right? And by the variance bias trade-off, you might tend to fit this only using a linear shape. It is not enough data for you to say you want to introduce another degree of freedom by introducing the bump there. Okay, so things like that will, if I'm fitting these two models separately for treatment and control, these two fit will introduce the bias when I'm really interested in the difference between the two. Okay. Then you might argue that in this case, we can just run experiments with 50-50%. So ideally, treatment and control should have the similar sample sizes, But however, once we have a lot of those covariate axes, there's always those subregions that treatment size and control size have significant difference. Okay, so if we don't do a good job adjusting this, your heterogeneous treatment effect estimator will be just kind of exploring these small sample size difference between treatment and control, and nail down those regions that treatment and control has the biggest sample size difference, and one overfit less than the other. So